Alright, next let's have a look at the last section of this topic, introducing derivatives. So remember that the derivative of a function at a certain point is defined using the limit of this function, fx plus h minus fx over h when h approaches 0, right? We have talked about this at the very beginning of topic 2. And this limit is called the derivative of fx at point P. Or we have another notation, fx prime or dy by dx for this particular limit. So there are two notations we can use. First, we can use fx prime, right? The derivative of a function fx is also a new function fx prime defined by this limit because we know at different points the derivative of function could be different, right? For each of the x in the domain, the derivative of the function at that point corresponds to the given x there. So this is also a mapping relationship. So the derivative of function is also a function. We call it derivative function or fx prime. And fx prime means the derivative of fx at any x value that is in the function's domain, whereas f prime at a or f prime a means the value of the derivative of fx at the point where x equals a. And fx prime is called the Lagrange notation. The second notation is called the Leibniz notation, which is dy by dx. It also means the derivative of a function. And if you want to denote the derivative of function at a certain point x equals a, then you can use this notation here, dy by dx when x equals a. Here. This means the derivative of that function at a particular point. And sometimes you could also use dy by dx, single bracket, single square bracket, x equals a. That means determine the value of the derivative when x equals a. Did you get it? And also note that the process of finding the derivative is called differentiation. When this limit is simplified by letting h approach 0, the resulting expression is expressed in terms of x. We can use this expression to determine the derivative of the function at any x value that is in the function's domain. So we'll use an example to illustrate the concept here. So suppose we have a function fx equals x squared. Can you state the domain of the function and then use the first principles definition to determine the derivative of fx equals x squared? What is the derivative's domain? So note that the derivative is also a function, right? And what do you notice about the nature of the derivative? Describe the relationship between the function and its derivative. Alright, now let's have a look at the solution. So according to the first principle definition, fx prime equals a limit of fx plus h minus fx over h when h approaches 0, right? Then we can insert x plus h and x into the expression of fx. So the numerator becomes 2xh plus h squared over h. H approaches 0 means h cannot be 0, so we can safely cancel h here. So you will end up like limit of 2x plus h when h approaches 0. When h approaches 0, this limit will approach 2x. Therefore, we know the derivative of the function fx equals x squared equals 2x, right? And its domain is also x belongs to a real number set. Notice that the derivative is also a function, right? So it's actually a mapping relationship between the input x and the derivative at this specific point x. The original function fx equals x squared is quadratic. Its derivative fx prime equals 2x, which is linear. The derivative represents the slope of the tangent or instantaneous rate of change on the curve. So we can substitute any value x into the derivative to find the instantaneous rate of change at the corresponding point on the graph of the original function. And also note that for limit, we have one-sided limits, right? And when we talk about continuity, we also talk about one-sided continuity. So similarly, we can also define one-sided derivatives, because derivative is defined using limits. If you have one-sided limit, then of course we will have one-sided derivatives, right? The derivative of function fx at any x value is defined by this, if the limit exists. Sometimes the limit only exists on one side. For example, the left-hand derivative of function fx at any x value is defined by this, which is the limit of this quotient when h approaches 0 from the negative side. So this is called the left-hand derivative. Otherwise, if you let h approaches 0 from the positive side, then that's called the right-hand derivative. Okay, next let's have a look at the concept of differentiable. A function fx is differentiable at point A if its first derivative fa exists. A function fx is differentiable on an open interval ab if it's differentiable at every point in this interval. And a function fx is differentiable on a closed interval ab if it's differentiable on an open interval a to b, and both the right derivative at the left endpoint exists and the left derivative at the right endpoint exists. Let f be a function that has a derivative at every point in its domain. We can then define a function that maps every point x to the value of the derivative of f at x. This function is written as f prime and is called derivative function, or simply derivative of f. Sometimes f has a derivative at most, but not all points of its domain. The function whose value at a equals f prime at a, whenever f prime a is defined and elsewhere is undefined, is also called the derivative of f. It's still a function, but its domain may be smaller than the domain of f. Okay, let's have a look at the connection between derivative and left and right side derivatives. So when we talk about limits, we know that the limit of a function at a certain point exists if and only if its left limit equals its right limit, right? Since derivative is also defined using limits, so we will have similar theorem, right? The derivative of this function at a certain point x equals d if and only if its left derivative equals its right derivative equals d. Also, a consequence of this fact is that if the one-sided derivatives are different at a certain point, then the two-sided derivative does not exist at this point, often denoted as d and e. Okay, next let's see an example to check your understanding of this concept. Can you find the left hand and then right hand and then two-sided derivatives, if it exists, of the function fx equals a square root of x squared at the point when x equals 0? Okay, note that for a function at a particular point, its left hand or left side derivative does not necessarily equal to its right side derivative. Okay, let's have a look at the solution together. So first of all, we can simplify the expression of this function. Fx equals the absolute value of x. When x is greater than or equal to 0, the expression of fx is x itself, right? On the other hand, when x is less than 0, fx equals negative x, right? So if you sketch the graph of the function, this is a graph of that function. It's a piecewise defined function, right? When x is greater than or equal to 0, you have this branch. Otherwise, when x is less than 0, we have another branch like this, right? So now we want to find its left derivative at x equals 0, which means f prime at when h approaches 0 from the negative side. So according to the definition of derivative, that equals f0 plus h minus f0 over h, right? And that equals fh minus f0 over h. When h approaches 0 from the negative side, that means from this side. We know that fh minus f0 will give you negative h, because h is less than 0, so you should use this expression. fh is simply negative h. f0 is 0. So basically you want to evaluate the limit of this expression when h approaches 0 from the negative side, and that equals 1, right? Which means when you approach 0 from the negative side, the instantaneous rate of change, or the slope of the tangent line of this function, is negative 1, which equals slope of this line, negative 1. And on the other side, when you want to find the right derivative when h approaches 0 from the right side, then you should use f0 plus h minus f0. The expression is the same over h. But this time, when you evaluate fh, note that h is a positive number, close to 0. So you should use this expression, fh equals h. So that equals the limit of h over h when h approaches positive 0, which gives you 1. So that means when you approach 0 from the positive side, the right derivative is the slope of tangent line, which equals the slope of this line, which is positive 1. And therefore you can see the left derivative does not equal the right derivative. So the derivative at x equals 0 does not exist. Specifically speaking, when x is greater than 0, the slope of the tangent line of this curve is 1, or the derivative equals 1. When x is less than 0, the derivative of this function is negative 1, but when x equals 0, the derivative of this function is not defined, because its left derivative does not equal the right derivative. Okay, so as you can see here, even at this point when x equals 0, the function is continuous, but it's not differentiable because its left derivative does not equal the right derivative, right? So next, we need to mention a theory that describes the connection between differentiable and continuous. Okay? Be careful. If fx is differentiable at x equals a, then fx must be continuous at x equals a. But the reverse statement is not necessarily true. If fx is continuous at x equals a, fx is not necessarily differentiable at x equals a. Okay? We have already seen a counterexample for the second statement. For example, this function is continuous at x equals a, but it's not differentiable at this point, right? And actually, we can easily prove the first statement as well. If a function is differentiable at a particular point, it must be continuous at that point. So for this course, you're not required to prove this, but I'll show you a simple proof. We can prove the first statement like this. If fx is differentiable at x equals a, then fx must be continuous at x equals a. So first, suppose that f is differentiable at a, then we have the following relationship. This is the definition of the derivative, right? F prime at a is the derivative of this function at x equals a. This is defined as a limit of fa plus h minus fa over h when h approaches 0. So this limit exists. At this stage, we find it convenient to write this limit in an alternative form so that its connection with continuity can become more easily seen. So if we let x equals a plus h, then h equals x minus a. So we can also express this limit as the limit of x approaches a of fx minus fa over x minus a. This is an alternative way we can express the derivative of a function at a particular point. So we can prove it's continuous at x equals a as follows. The limit of fx when x approaches a will equal this expression, right? And then we can detach it to a limit times another limit plus the limit of fa when x approaches a. So this gives you the derivative of this function at x equals a times a minus a, which is 0, plus fa, which equals fa. Therefore, you have proved the limit of this function at this particular point a equals the image of this function when x equals a. Therefore, this function is continuous at that point, right? Okay. And for the second statement, again, we have already seen a counterexample. So this function fx equals the absolute value of x is continuous at x equals 0, but it's not differentiable. Okay? So you should remember this. If a function is differentiable at a particular point, it must be continuous at that point. But reverse statement is not necessarily true. You see that? Next, let's have a look at some cases where the derivative does not exist. So these are the typical cases where usually we don't have derivatives. Given a function y equals fx, the derivative does not exist at x. If there is a discontinuity, for example, at the point x equals x1, x2, x3 in the first diagram, or vertical tangent, for example, x4 here, cusp, for example, x5 here, or corner, for example, x6 here, as shown in the following diagrams. We say that f is not differentiable at such x values. Okay, there are 4 typical cases where function does not have a derivative: discontinuity, vertical tangent, cusp, or corner. Sometimes one encounters a point in the domain of a function y equals fx where there is no derivative because there is no tangent line. Remember, derivative is actually the slope of the tangent line, right? So in order for the notation of the tangent line at a particular point to make sense, the curve must be smooth at that point, in a summary. This means that if you imagine a particle traveling at some steady speed along the curve, then the particle does not experience an abrupt change of direction. There are 4 types of typical situations we should be aware of, namely discontinuities, vertical tangent lines, corners, and cusps, like this. Okay, so that concludes the second topic, and make sure you can finish all the homework. Okay, we'll have a look at the homework questions at a later time.